All right, so for this week, we are working on chemistry, and hopefully, this looks familiar to you. This is the periodic table. So, this is the table that has essentially every element that is found on Earth. So, whether that be iron, which you see here in brown, whether it be magnesium, sodium, potassium, or calcium, even oxygen that we're currently breathing in right now, all these elements are found on the periodic table. So some of these elements have, even though this is iron, but it's represented by the element symbol of Fe. So again, all of these are elements, but some of these have different names than we're used to seeing. So even though this is sodium, but it has an Na. So some of these elements are from a Latin root, and so some of them kind of kept their names in order to not be able to be confused with some of the other elements. So with elements, they have some numbers around them as well. So like one for hydrogen, that's up here, it has an atomic number of one. So the atomic number actually means the number of protons that it actually has. And so instead of saying protons, they use atomic number. The atomic mass is actually a combination of the protons and the neutrons. So once we get into this chapter, we'll actually use a little bit more of that terminology so that you actually understand what's going on. Another way to understand the periodic table is that on the left-hand side of the periodic table, which would be this side here, would have most of your metals that you're commonly used to seeing. And yes, sodium is actually a metal. Now, the substance that we eat that we call salt is actually called sodium chloride. So it's actually a combination or compound that's made of sodium, the metal, and chlorine, the gas, which makes the table salt that we eat. So typically when we say sodium, we're thinking of sodium chloride. However, sodium itself is just a metal. Also with the periodic table, you have metals, the noble gases, which is in the far right side of the periodic table. These gases don't like to react with anything, so that's why we call them noble. The ones that you see highlighted are actually the elements that are commonly used within our bodies. So matter is essentially defined as a substance that has mass and occupies space. So this could be present in a solid, liquid, and a gas form. And so all these elements are either solid, liquid, or gas. So common elements that are found in the human body, so they actually break it down into major elements. So oxygen at 65%, carbon, hydrogen, nitrogen, calcium, and phosphorus. Now there's also some minor elements that are found in us, such as sulfur, potassium, sodium, chlorine, magnesium, and iron. Now just because they only make up 1% of our body weight does not mean that they're not important. We need all of these. If you've ever heard of the term electrolytes, that's what they're referring to. So some of these are actually some of our electrolytes. So if you drink Powerade or Gatorade, you are actually ingesting some of these elements into you. That's actually going to help your body. You need it for muscle contraction and also for your nervous system, and they're able to conduct electricity. So that's why they're called electrolytes. And we'll see that further down in the chapter. But here are some of the basic elements from the periodic table that we actually have to have on a daily basis. So, to better understand the atom, so we need to be able to break it down an atom. So an atom is the smallest piece of matter that we have. Atoms are made out of three different things: protons, neutrons, and electrons. And they are actually here inside the middle of that atom, which is called the nucleus. So the nucleus is actually composed of protons and neutrons, as you're seeing right here on the screen. And then the electrons are on the outside of the atom. Now, also understand that protons have a charge of, or have a positive charge. So protons are easy to remember because positive starts with P, so does proton. Neutron Neutron sounds like neutral, and neutral means essentially zero, and neutrons have a overall charge of 0. Electrons have a negative charge. So let's go back through that. So protons have positive, so P for positive, N for neutral, or for neutrons, and then electrons are negative. Now, you might be asking, why is that even important for you to understand? Electrons, which are outside, are essentially what are essential for making things bond. So if you think about sodium chloride, which is our table salt, the electrons on each element in the sodium and the chlorine are actually bonding or having a type of bond to each other. That's what allowed them to come together. If not, they just stay separate as a metal and a gas. So again, a proton has a positive charge, a neutron is uncharged, and those together make the neutron, or make the nucleus, which is going to give you the mass number. So your protons and neutrons are what's going to give you that mass number that you see in your element symbol. So your atomic mass is made out of your protons and your neutrons. And then your atomic number is your protons. So there's also a such thing called as isotopes. So isotopes are where you have an element that has a different number of protons. You have a different number of neutrons. Protons never change. So if you change the number of protons, you have changed the element. So if we scroll back up, if you remember me saying that the atomic number is the amount of protons it has. So if I went from atomic number of 1 and changed it to 2, which means I have 2 protons, that changes the entire element. And you see that it becomes helium now. If I had an atomic number of 3, it'd now be lithium. So if you change the atomic number, which means if you're changing the amount of protons, you're changing the element. However, if you change the amount of electrons or neutrons, it can still be the same element, because those don't necessarily define the element. But what does define the element is the amount of protons it has. So an isotope is changing the number of neutrons that it has. So if you look here, so carbon naturally has 6 protons, 6 neutrons, and 6 electrons. But in carbon-13, it's still carbon, which means it has 6 protons. However, it has a different number of neutrons. If you look from this one, this is 6, this one is 7. So if you add 6 and 7 together, you get 13, which is its atomic number. It's its mass number. For carbon-12, if you add 6 protons and 6 neutrons, the mass number will be 12, ergo the number 12. Same thing with carbon-14, you still have 6 protons, which means that it's still the element of carbon. However, the number of neutrons change, so 8 and 6 together, if you add those or combine those, you get 14, which is the mass number. So if you notice in all of these, the atomic number or the amount of protons stay the same. Therefore, the element carbon is the same across each. However, the amount of neutrons changed. But why is this actually important? So, if you change the amount of neutrons, it actually changes some characteristics about that carbon. So when we look at carbon dating, so like if we took a fossil and we were trying to track back how old this fossil was, we'd use one of these carbons here to actually help us date back to and give us an accurate representation of how old this specimen was. So it's still carbon, it's just a different consistency of carbon, essentially. When it comes to radioisotopes, which Essentially, these isotopes are radioactive and release radiation as they decay into a more stable isotope. So carbon-14 is actually an example of that, and so that's what we use for dating. So in comparison, the time required for half of the radioactive material to be eliminated from the body is referred to as biological half-life. So that is how they're actually able to track back how long something has been dead or how long ago it lived. So this can be used in medical imaging, especially like if you're having thyroid issues. They can give you carbon-14, which is one of the isotopes up here. They can give you iodine 123 or phosphorus 32. Those isotopes are used for essentially treating thyroid issues. I actually had a friend who actually had thyroid issues, and they gave her iodine, which is very, very toxic. And essentially, it was helping to decrease the size of her thyroid because it was a little too overactive. So we also put iodine in our salt. So the regular iodine is fine, but if you start changing the amount of neutrons, you change some properties of that element, which means it can react a little bit differently. So isotopes are very, very important. Depends on what you're using. So in chemistry, we talk about the octet rule, which octet, that prefix means 8. So most outer shells, which is where the electrons sit, like to be full. They like to have essentially 8 electrons in their outer shell. Ergo, the name octet rule. So the number of electrons in the outer shell is referred to the valence electron shell. So this just means that it's the amount of electrons that are left in the outer shell. So here gives some examples. So we can see here the valence electrons are in the outer shell, not the inner shell, but the outer shell. So in carbon has 4 valence electrons. So it has 1, 2, 3, 4. So when we're referring to valence electrons, it's referring to the outer shell. So of course, carbon has 4. Beryllium over here has 2, and hydrogen just has 1, and lithium has 1. And if you also notice down here, sodium, or Na, or sodium, has just 1 electron in the valence shell. This is very important because valence shells are what allows other elements to be able to bind. Remember, the outer shell wants usually 8. And this has 4 in carbon here, so that means it can bond 4 more times with 4 other electrons. And that's one reason carbon is so versatile, is because it has 4 valence electrons. And if they are, and like as I hear with the octet rule, atoms that obtain an outer shell with 8 electrons are very stable. And that is what elements want, or atoms want. They want to be as stable as they possibly can. If you remember me saying earlier, noble gases are noble because they are completely full. Their electrons or valence shells are completely full, so they don't want to bond with anything, so they kind of like to be by themselves. Ergo the name noble gases. So there's different types of ions or compounds. So you have what's called an ionic bond. So ions are essentially either they're plus charged or negatively charged. So let's take sodium chloride, for instance. So sodium, if you notice right here, sodium has a plus charge on it. That's where it has why it says plus. If it says that it has an overall plus charge, that means it has more protons than electrons. If you remember earlier saying protons have a positive charge and electrons have a negative charge. So if sodium has a positive charge, it means it has more protons than electrons. And in this case, it just has 1 more proton than electrons. So if you notice, there's not a number beside that plus sign, which just means that it's understood to be 1. Now with like magnesium or calcium down here, you see that there's a +2, which means it has 2 more protons than electrons. Now let's do the reverse. If it had 2 more electrons than protons, then it'd have an overall negative charge. So if it has a positive charge, that means it's an ion or a cation. That's up here. So ions with the positive charge are called cations. How I remember cations, cations has a T in it, and that T looks like a plus sign. So cations are positive, whereas ions that have a negative charge are anions. So like chlorine, which means it has 1 more electron than proton, it has an overall negative charge. So that would be a anion. So a cation would have a positive charge like magnesium, and an anion would have a negative charge like chlorine. So what makes it an ionic bond? So by giving up or donating that electron that's in their valence shell, sodium has a complete valence shell. So let's look at this diagram here. So chlorine has sodium has 1 electron in its outer shell or its valence shell. Remember, each shell wants to have 8, but sodium's outer shell only has 1. So, and if you notice here in the next shell down, it has 2, 4, 6, 8. So that last shell is actually full. However, this very last shell here, it's quite empty, it only has 1. However, if you notice over here, chlorine has 2, 4, 6, 7. So it's easier for chlorine just to gain 1, and it's easier for sodium to give away 1 instead of gaining 7. So what sodium is going to do is just donate this electron to chlorine. Once it does that, sodium now has 1 or 2, 4, 6, 8. It is happy now. It has 8 in its outer shell, and chlorine now has 2, 4, 6, 8. And it has 8 in its outer shell. So now they're both balanced. They both satisfy the octet rule. They're both happy. So this is what's called an ionic bond, when one element donates or accepts an electron from another element to where both elements are now satisfied. That is called an ionic bond. And also, this is what happens when sodium, the metal, and chlorine gas come together. We now make table salt. I know it's kind of crazy to think about that a metal and a gas come together and make a salt, but that's how we actually get it. So now you understand an ionic bond. So when we think of salt, we always usually think of table salt that we put on our food. However, a salt is just the binding of a cation and a negative, or cation and an anion. So magnesium and chlorine binding together would be a salt. So if you've ever used Epsom salt, which is a salt compound that is used to help with soreness or muscle aches, that's a salt. The salt that they use to salt the roads when it's cold and it's winter outside, that's a different type of salt. It's not the same salt that you actually eat. The salt that we use to put in our food is sodium chloride, or iodized sodium chloride. However, if we were to put Epsom salt, the salt that we use for our sore muscles, in our food, it actually gives us diarrhea. So we tend to use salt very loosely, but salt just means the binding of a cation and an anion. That is what a salt is. So you have other types of salt as well. You have magnesium chloride, and you also have what's called calcium phosphate. Now, calcium phosphate is actually what is responsible for hardening our bones and our teeth. Now, do understand, teeth are not considered bones. Even though they are made out of the same materials, it actually lacks one of the materials. And so it's not considered bone, but they are both made out of calcium phosphate, which is a salt essentially, and it's what makes our teeth kind of hard as well as our bones. And we want those to be hard. So now that we've talked about ionic bonding, we need to talk about covalent bonding. So covalent bonding is sharing electrons between two atoms, and that results in a covalent bond. So let's think about water. So we always know water is H2O, which means there's two hydrogen and one oxygen bound together. That is called a covalent bond. So if you remember, it said sharing of electrons versus ionic bonds was donating or accepting a electron. So think about covalent bonding as these two elements actually holding hands. So down here, we actually see the difference between covalent bonding. So here we have two hydrogens put together. Instead, in ionic bonding, where the hydrogen would donate its electrons, they're sharing their electrons. So this is like these two are holding hands, and by them holding hands, their hands locked together is what's creating that bond. So it's a pretty strong bond. And a double covalent bond, so in the oxygen gas that we are actually breathing in right now, it's a double covalent bond, which means that they're sharing two sets of electrons. So let's count how many electrons are in its outer shell. You have 2, 4, 6, 8. Now let's go to this other oxygen, 2, 4, 6, 8. They're actually sharing 4 electrons between the two. So this is what covalent bonding is. It's a lot stronger bond to each other. And a triple covalent bond, they're actually sharing 3 sets of electrons, which means it's a really tight bond. So in some compounds that we might actually know, like methane, so if, especially when someone passes gas or a silent but deadly gas, this is actually a big chemical component in it. So if you look here, you have a single covalent bond. So you have 2 here. So carbon has 2, 4, 6, and 8. It is satisfied. And then that first ring, in the first ring of any element, there can only be 2 electrons. So hydrogen only has 1 ring, and it has 2, 2, 2, and 2. So everything is nice and satisfied and balanced. Carbon dioxide, the compound that we're actually breathing out. So we breathe in oxygen, but we breathe out carbon dioxide. It has double covalent bonds. If you look between the carbon and the oxygen, it has 2, 4, 6, 8. The oxygen has 2, 4, 6, 8. So the outer rings, or the valence electron shell, each one is satisfied. Ethanol is actually the chemical that is responsible for Friday night activities. So if you go out to a bar and you're drinking beer or drinking wine, this is the actual chemical that is actually giving you the wanted feeling or the buzz or the inebriation. So this is the chemical that's responsible for that. This chemical is also found in our gas. So anytime you go and pump gas into your vehicle and it says 10% ethanol, it's referring to this material. So yes, the chemical that you drink on a Friday night is the same chemical that you put into your vehicle to drive to place. But if you look at the element here, everything is satisfied. It has double covalent bonds. So it's a very strong molecule, and it's also strongly bonded to each other. So Even though that this is a nice pretty picture, there's a simpler way to draw these. So you can simply just draw a C for carbon, and then you have 4 H's, and then these lines that are going from each letter are actually representing bonds or covalent bonds. So instead of having to draw this big structure, you can simply just draw this C and 4 H's and draw some lines that goes to each H or to each element, and it is understood to be the exact same thing as this. So sometimes you might see it look like this or look like this, but most times it's going to look in a stick structure just because it's a lot easier to draw. So with double covalent bonds, we also call that a double bond. That's why you see 2 lines here. And if there's a triple bond, you see 3 lines. So let's get a little bit more complex. So you have what's called a straight chain, a branch chain, and then a ring. So straight chain goes with its name. It is in a straight line. So you see all these carbons and hydrogens linked to each other with a double covalent bond, or also known as a double bond, which the book gives a really good way of breaking this down. So instead of drawing out this long carbon chain, you can simply draw it like this. So each carbon, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. You can simply draw it like this structure down here, which this one looks a lot different than this, but it is the exact same. So each point is a carbon, and here you can see the double bond, and each point is still a carbon. So let's count how many carbons we have. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is the exact same structure. You can also see that the double bond is in the exact same spot. So if you see something like this, don't freak out. They've just condensed it. It actually looks like this. So some people get really scared when they see this structure here or something drawn like this, except it's just a lazy way of drawing this. So that was a straight chain. A branch chain sounds just like it is. It's branching. So you see that there is a linear figure here, but you see branching from this linear figure. Also, you see it here and here. So that just means it's growing wider. And here's another way to write that branch chain. A ring structure just means that it's in a circle formation. So we have 6 carbons here, 1, 2, 3, 4, 5, 6. So you have 6 carbons. Instead of drawing it like this, we can simply draw it like this. Usually when they draw structures like this, they leave off the hydrogens because it's understood that the hydrogens are there. We know that carbon bonds to 4 different things. It has 4 valence electrons. So we see carbon has 1, 2, 3, 4 things attached. So we automatically know that these carbons have either hydrogens or it's attached to another carbon. Electronegativity, which is just another way to say how strongly that these elements are able to pull towards each other, or how strong these elements are, or how strong like a magnet it can pull. So electronegativity is going to essentially show us how well it can attract another element. And why is that important? It's because some elements are going to be harder to break apart if they have a higher electronegativity. If they don't have a high electronegativity, they're easier to break apart. So 2 atoms of the same type, such as 2 hydrogen atoms or 2 oxygen atoms or 2 carbon atoms, are identical in the chemical structure and thus have the same attraction for electrons. Consequently, the 2 atoms share the electrons equally, which results in a non-polar covalent bond. So if something is polar, there means that there's opposites. So if something's polar, it's like a magnet. Remember, a magnet has a positive end and a negative end, or a north pole and a south pole. So that means that they're opposite. If it's nonpolar, that means that they are the same, which means that they don't have an attraction to anything else. It's just kind of there. A polar covalent bond, which means they are different atoms, which means they have a different electronegativity, which means one end is stronger than the other end, or one end is positive and one end is negative. So to be able to denote that, they write a Greek letter of delta with a plus or minus, and it kind of looks like this. So also that is also termed as a dipole, which means it's just showing how those charges are moving. It's also showing how if something is more positive, is it moving towards something more negative, or is something more negative moving towards something more positive? It's just showing us how, it's just basically showing us if there's movement. So a better look at that is looking at this sugar molecule in water. So water is very polar. So polar means you have a positive end and a negative end. So those hydrogens are positive, notated right here with this delta sign with this plus. Oxygen is very negative. It's electronegative. So it has these delta negative signs. So these negatives is going to be attracted to positives. That's why you see this little dashed line here. So you see it's negative, it's attracted to positive. And you'll see in others where you have positives over here attracted to negatives. So those are just showing us that of how this water is interacting with this glucose molecule. So why this is important when it comes to being hydrophobic or hydrophilic. So hydrophobic, so if you break the word apart, hydrophobic means, hydro means water, phobic means fearing, like a phobia, like if someone has a phobia of spiders. So hydrophobia just means that it is scared of water or doesn't like to mix with water. So you can think about this as being like oils, butters, fats. It doesn't like to mix with water, so we call that hydrophobic, which is a resultant of non-polar molecules that are placed in water with other polar substances. So water is polar, but oil is not. So those don't like to mix. If you have polar, that means that it's going to mix very well. So like if you're trying to dissolve salt and water, well, sodium is positive, oxygen is negative, and then chlorine is negative, and hydrogen is positive. So those are attracting to each other, and they're being able to be spread apart, and that's how it's actually dissolving. So organic molecules are defined as molecules that contain carbon, and these are components of living organisms. So with water being composed of one oxygen atom bonded to two hydrogen atoms, it exhibits polarity because there's an unequal sharing of electrons. So if you look here we see these symbols again. You got negative because of the oxygen bonding to the positive of the hydrogen. So that's why they are arranged in this certain fashion, is because remember, negative is attracted to positive and positive is attracted to negative. If they were both positive, it'd be like trying to put two positive ends of a magnet together. They would repel each other, kind of like oil and water. However, with negative and positive charges, if you flip that magnet around, they'd actually stick together. So that's why it's important to understand what is negative and what is positive. So water actually has some unique properties. So of course it can transform from a gas, liquid, and a solid. However, if you've ever noticed that when you freeze something, that water will take up more space. So if you put like a water bottle in the freezer, it might be, the water bottle will be a certain size, but after it freezes, it expands. So water is one of the only fluids on Earth that actually does this. So water, and how it actually does this with how their electrons and their bonds actually um, form and separate from each other. But water also has some other properties. So it's able to transport. So the biggest component of our blood is actually water. So we think of blood just being this red liquid, but it's actually a lot of red blood cells that are suspended in water. So a lot of that water has a lot of our salts that are dissolved in our bloodstream. And so it's able to transport fluids and hormones and other proteins to everywhere in our body. So it has a big portion to do with that. It's a lubricant or lubricating fluid. So it actually helps decrease friction. So our heart and our lungs, they sit in this sac that protects each other from each other. So just like in the previous video, the pericardium actually reduces friction. It protects it from being rubbed against the lungs, and also protects the lungs from rubbing up against the heart. Also, our brain is floating in fluid. So if you were to slip and fall, remember that your brain is this soft tissue and your skull is a very hard bone. So you have to have something in there to cushion the blow, or if you were to fall, it cushions your brain from slapping up against the side of your skull. If that does happen, we end up calling that a concussion. And so it can cause a few different issues. And then also, we also excrete water. So water is also used in our bodies to get rid of some substances. Fun fact is that when you're peeing, you're actually peeing out a big component of your bloodstream. Your kidneys separate the water from the red blood cells, and what that water that's separated out, you pee out. So you're actually peeing out your blood, essentially. Water also has a high surface tension. So if you've ever tried to balance a paperclip on top of water, or if you've ever seen an insect walk on top of water, it's because those hydrogen bonds, they are sticking together. And so insects can actually walk across it without breaking those hydrogen bonds. Or if you've ever been swimming and you've stood on the edge of a swimming pool and just fell over or belly flopped in there, it hurts because there's a lot of surface tension because of all those hydrogen bonds sticking together. Also, that's referred to as adhesion. So you can think of adhesion as being like adhesive, like that's on tape. It makes things stick together. So when you put like a water drop on a table and it stays there, that's due to adhesion. Or cohesion is where you have water droplets. If you put two water droplets side by side and then you move them together, they come to make one water droplet. That's actually cohesion. But adhesion is just essentially just where it just adheres to the side of something. So if you wash your dishes or even in your water bottle and you see those little bits of water that's stuck to the side, that's due to adhesion. That is actually the molecules, the hydrogen molecules of the water actually being stuck to the molecules of the water bottle. So that's actually a bonding that's actually happening in your water bottle. So when people think of chemistry, they always think of something blowing up, but even the water that's stuck on the inside of your water bottle is considered chemistry. So a clinical way to look at water or surface tension, our lungs kind of depend on surface tension. We have a chemical in our lungs that's referred to as pulmonary surfactant. That's what you're seeing right here. So essentially, it keeps the air sacs in our lungs lubricated. Typically, with babies or children that are born premature, they are lacking this surfactant, which makes it very difficult for them to breathe. That's one reason why you have to put them in an incubator to keep them separated from everyone. Remember, the lungs are the last organ to develop. That's one reason why babies will cry, and why it's good for them to cry, because their lungs actually start developing, actually working during that point, because they can't work while they're in the womb and all the water in the amniotic fluid. So once they are born or pushed out the canal, they start crying to get rid of that fluid, and then their lungs finish developing. If they're premature, which means they did not finish developing while they were in the mother, they're not going to finish developing right after they are born. So that's why they have to be put in the incubator. So water has a really big part of our body. We're made out about 72 to 76% of water. So that's one reason why it's very crucial that you drink enough water. Water is also good with temperature regulation. If you notice, if you ever get too hot, you start sweating. You sweat, your body releases water, because water is able to take in a lot of heat. And if it's able to absorb that heat, it's cooling you off. So if it takes away the heat from your body, and then that water is evaporated by your environment, that's what's actually cooling you down. So you don't sweat because you're hot, you're sweating so that you can cool your body down, so the water can absorb the heat so that it can cool your body down. And water also has what's called a specific heat, which means it's the amount of heat that water can absorb. So that's one reason why in our cars or our vehicles we use coolant, which usually you see it's 50-50, which means it's half water and half coolant, because water can absorb a lot of heat, but coolant can absorb just a tad bit more than water can. And then heat of vaporization is the amount of heat that it can take, that it can actually turn from a liquid phase into a gas phase. So when boiling water has to be at 212 degrees Fahrenheit. And the reason is because it's trying to break all those hydrogen bonds. It takes a lot of energy to break those covalent bonds. They are very strong. So that's one reason why it takes so long to boil water, is because you're trying to add enough energy to break those bonds apart. And that's what you're actually seeing when water is boiling. You're actually seeing bonds being broken. So in terms of solvent and solutes, so if I were to take some salt and then dump it into a cup of water, the salt, or the sodium chloride in this case, would be the solute, and then the solvent would be the water. So solvent is what is being used to be dissolved in, and then solute is what you're actually putting into something to be dissolved. So again, solvent would be what the liquid is that you're going to be pouring something into, which would be the water, and the solute is the chemical or powder or substance that you're going to be pouring into something that needs to be dissolved. So it could be sugar, it could be salt, it could be tea. So that would be your solute. So we talked about hydrophobic, but the opposite of that would be hydrophilic, which means water loving. So in order something to dissolve, it has to be hydrophilic. If it's hydrophobic, it just means it does not want to interact with water. It's scared of water. It doesn't want to have anything to do with it. Hydrophilic means that it loves water. So in order for something to dissolve, it has to like water, of course. So that what you're seeing here with glucose, when you dump sugar into some water, you're seeing the oxygens react with the hydrogen, which is positive, the oxygen is negative, and so forth. And so that is how what's called a hydration shell. So essentially all these water molecules actually kind of swing around the glucose, kind of like it's getting ready to attack it, and actually starts bonding to it. And that's how things are able to dissolve. So when something dissolves in something, it's actually reacting with the water, or with the positive and the negative components of the water, and that's how something's able to dissolve. So in the case of dissolving sodium chloride in water, sodium chloride is an ionic bond. However, when you put that into water, it actually separates or dissociates the sodium from the chlorine. So it actually is going to split these apart. That's why you see them far apart here. If you notice here that the negative, so that sodium is positive, but you see that all of these water molecules are turned with the kind of Mickey Mouse ears, or the hydrogens facing outward. So remember, oxygen is negative, and it's going to be attracted to things that are positive, which would be the sodium. If you look down here, you notice that the hydrogens, or the Mickey Mouse ears I like to call them, they're positive. They're going to be attracted to things that are negative, and the chlorine is what is negative. So that you see that they actually start forming around, kind of like getting ready to gang up on this poor little chlorine here. That's what you're actually seeing. You're actually seeing how they are interacting with things that are negative and which are positive. So if it's polar, that's one reason why we talk about things being polar. We need to be able to see if something is positive and negative. If we know it's positive and negative on one end, that means that it's most likely going to dissolve. So this is actually what's happening when you dissolve sugar in water, or even salt in water. It's the water is reacting with it by surrounding things that are positive and surrounding things that are negative, and they're actually breaking them apart or separating them. Now that was with polar molecules. With hydrophobic molecules, these are nonpolar, which means that they don't have a positive and negative charge. So this would be like vegetable oil in water. Vegetable oil is going to sit on that very top layer because it doesn't want to have any interactions with water. It doesn't like it. It's hydrophobic. It's scared of it. So it's afraid of it. So it wants to get as far as possible away from it. So it's not going to dissolve. So if there's no positive or negative that the oil has, there's nothing for the water to actually be attracted to. The hydrogens don't have a positive or negative to be attracted to, and the oxygen that's negative doesn't have a positive to be attracted to. So there's nothing that it can bond to or break apart. So nonpolar is going to be hydrophobic, and there's nothing it can do to actually separate it. Same thing here in a phospholipid bilayer, which we'll see when we get to cells. The tails are going to be hydrophobic. So no water that's on the outside can really get to the inside of the cell. But the outside of the cell is hydrophilic, which means it likes water. That's why you see water molecules with here. But the inside of those tails, which they are facing each other, so they make a membrane or phospholipid bilayer. Here go the name bilayer, means two layers. This internal environment does not like water, so it shuts water out. So it keeps water in, it keeps water out of the cell. So another way to look at this is hydrochloric acid, like the acid that's found in our stomach. If you were to put that in water, it actually dissociate, which means it would split it into hydrogen and chlorine. If you notice right here, hydrogen is positive, chlorine is negative. Water has to have something to be attracted to. So if there's no attraction, it's not going to be able to pull it. However, hydrochloric acid has a positive hydrogen and a negative chlorine. So substances that both dissolve and dissociate in water, such as salts, acids, bases, can readily conduct electric currents. So this is what we call electrolytes, because they conduct electricity. This is one reason why they tell you to drink like Pedialyte or Gatorade. They have electrolytes in them. It's like your magnesium, your chlorine, your sodiums. If you notice, all of those have a positive or negative charge. Ergo, it takes positive or negative charges in order to generate electricity. So if you think about your phone that you plug in at night, Electricity is just the flow of electrons moving. So when you plug in something, electrons from your wall outlet travel into the phone, and then they travel back into the wall. So everything around us that you see is made out of those elements on the periodic table. Everything that we see or touch has electrons, protons, and neutrons. If you don't believe me, think about this. When you go outside and you have really curly hair and it's humid outside, there's a lot of water molecules in the air. And then your hair gets frizzy. Well, that's actually the water molecules in the air reacting with the protons and electrons that are in your hair. So that's why they get frizzy. So everything that we see, everything we have in this world is made out of the elements off the periodic table, which means they have protons, neutrons, and electrons. So, acids and bases. So an acid is a substance that is going to dissociate in water and produces both an H plus or hydrogen and an anion. So essentially, an acid is a proton donor or a hydrogen donor. Remember, hydrogen is just one proton. Its atomic number is 1. So it's hydrogen is literally just one proton. So that's why you also hear it called a proton donor or an H donor. Strong acids dissociate to a greater extent and produce more H positives than weak acids. So you have a weak acid produces some H's or H positives, but strong acids produce a lot more H positives. So like our stomach acid, which is hydrochloric acid right here, that's secreted by our stomach, is a really strong acid. It's used for breaking down proteins. Weak acids, such as carbonic acid that's within our bloodstream, they are kind of weaker. They're still, don't get me wrong, they're still kind of strong, but they're weaker than some acids. A base is the opposite. So acids give away hydrogen, bases accepts hydrogen, also known as a proton acceptor. Strong bases dissociate a greater extent and bind more H positives than giving off H positives. So an example of this that's in our household would be sodium hydroxide, which is what you see right here, which is notated by sodium OH or oxygen and hydrogen. So that would be essentially like drain cleaner or drain max or Drano. That is the active ingredient in those chemicals. Also, another base would be baking soda. That is a base, or also known as sodium bicarbonate. That is a base. An acid that we actually use, and it's actually kind of a weak acid, is vinegar. Vinegar is actually a weak acid. Another acid that we might use would be lemons. Lemons or fruits that have citrus or citrus fruits have a lot of acids. That's why they always tell you make sure you brush your teeth after eating acidic fruits, because it can actually start eating away at your teeth. Because remember, your teeth is made out of a salt, which is just an anion and a cation, which means it has a positive and negative charge. Also, it's able to dissociate. It's able to start giving more protons, which means it can start breaking down your teeth a lot quicker. So keep that in mind next time you're eating fruits or acidic fruits, or eating things with vinegar or pickles. They're very acidic. If it burns, it's pretty acidic. Another example of a base would be bleach or milk. Soap is actually a base as well. So if it's a liquid, think about if it's an acid or a base. So the pH scale goes from 0 to 14. So anything that's in between a 0 and a 6 is considered a acid. So anything from 0 to 6.99 would be considered a acid. A 7 is referred to as neutral, so that would be water. And then basic is anything that's after 7 to 14. So here are some examples. So also understand that when it gets closer to 0, it means that it's really acidic. When it gets closer to 14, it means it's very basic. So if we look here, acidity is increasing. So the least acidic on this level would be milk. That's one reason why it's kind of almost considered kind of basic, because it's a very weak acid and a weak base. But urine has a pH of 6. Tomato juice has a pH of 4.7, which means it's pretty up there. It's getting pretty acidic. Lemon juice and our stomach acid is actually the same concentration, the same pH, as well as hydrochloric acid. So the more closer you get to 0, the more acidic that it gets, the more harmful it can be. So let's take a look at our base scale. So our blood actually stays in between a range of 7.3 to 7.45. So it's a very narrow range that our blood pH can be. Antacids, so if you have an upset stomach, which means that the pH of your stomach is very low, if we want to stop making it so acidic, we're going to increase our pH, which would be, is why we give it an antacid. Antacids increase our pH of our stomachs, so it makes it a little bit more basic. Bleach, like I said earlier, would be pretty basic, as well as sodium hydroxide is one of the most basic. So when I refer to pH, pH stands for potential of hydrogen. If you remember how we said that acids are proton donors, means it gives off more protons or more hydrogens, this is what it's referring to. It's the potential of hydrogen. Essentially, it's looking at how much hydrogens are in that substance. So the pH scale represents a 10-fold change. So when we're looking at the pH scale, we say it goes 0 to 1. To us, that doesn't really mean anything, because that's the next number up. However, that actually means that it's 10 times worse. So if we went from 0 to 1, that's 10. And then 1 to 2 would be 10 times 10, which would be 100. And then 2 to 3 would be 10 times 10, which is 100, times 10, which would be 1,000. So it increases by 10-fold. So from going from 6 to 5 may only look like 1. That's only decreased by 1, but it's actually decreased by 10, 100, 1,000, 10,000, 100,000, a million. So it actually increases by 10. So it's actually very, very, very acidic. And as you go down here, it's very, very basic. So we simplify it to be 0 to 14. However, a jump between each of these numbers is actually multiplying by 10. So water mixtures. So we have mixtures and then emulsions. So like I said earlier, when we take our blood, it's really just a bunch of red blood cells suspended in our water. But if we put it in a centrifuge and actually spin it and separate it, all the red blood cells go down to the bottom. The white blood cells are going to stay in the middle, which we refer to as leukocytes, because leuko, that prefix means white, cyte means cells. And then the plasma is the water component with the proteins and our ions and our electrolytes in it. So that's why we refer to it as plasma and not water. So that would be referred to as a suspension. A colloid would be kind of like a gelatinous mixture that's actually found within our cells. So when we get to the cell chapter, the cytoplasm is kind of a colloid mixture. Also kind of the same thing that's in our thyroid. And then a solution would be an example of that would be kind of like a soda, where you have things mixed together and it's kind of homogeneous throughout. So that's like if we mixed sugar and water together and dissolved it, it would still look like water. So that would be termed as a solution, because also we can also still separate soda and water, or sugar and water. We could separate it out. We could dehydrate the water out of it and have the salt. So that would be a solution. An emulsion, however, if you remember earlier, we said that water and oil do not mix. However, if we shook this vial very, very vigorously, we can make it what's called an emulsion, which means there's a bunch of particles of vegetable oils that are kind of really suspended throughout here. So that would be what we call an emulsion. So biological molecules. So these biological molecules are large organic molecules. And organic just simply means that it contains carbon, hydrogen, oxygen, and sometimes nitrogen. And so I know that if we go to the store and we say that these are organic, what that actually means is that it was grown without other chemicals and things added to it. But do understand, when we are in chemistry, organic just means carbon, hydrogen, oxygen, and nitrogen, which everything that's living or that we're able to consume is made out of carbon, hydrogen, oxygen, and nitrogen. So sometimes there is some misconceptions about what organic actually means, but organic in chemistry means that there is carbon, hydrogen, nitrogen in it. But organic, if you buy something from a store or something's grown organically, it's a synonym that just means that it is not grown with other additives and pesticides and things of that nature. So hydrocarbons, if you break that word apart, hydro means hydrogen, carbons meaning carbons. So it literally just means that there's just a bunch of carbons and hydrogens linked together. So that's what you're seeing here. So you're seeing carbons or bonded to each other, and you're seeing carbon and hydrogen bonded to each other. So consequently, because it's carbon and hydrogen, especially if there's long chains of carbon hydrogens, they're hydrophobic and they're not very soluble in water. So the more carbons and hydrogens that you have in that chain, the less likely it's going to be able to dissolve. So think about oils and waters. Oils have a lot of carbons and hydrogens, and they do not like to bond very well with water. So they're hydrophobic. So here are some organic or functional groups. So like hydroxyl, which is just an OH. So anything that has an OH, like an alcohol. So like the alcohol that you drink is C2OH, which OH just means it's a hydroxyl, or means it's an alcohol. So you can find these in carbohydrates, proteins, nucleic acids, and lipids. This structure here is glucose. So you see there's many hydroxyl groups in there. Also, this is what is essentially polar and allows for water to bind to it and dissolve. You have a carboxyl, which is carboxylic acid. So carboxylic acid also has a double bonded oxygen and then one bond of a hydroxyl group. So this can be found in proteins and lipids. So if we look at this fatty acid here, how I said that oils and things of that nature, or fats, have a lot of carbons. So if you look 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, that is a long chain of carbons. So this is not likely to dissolve in water. So the more carbons it has, the less likely it is to dissolve. So here's an actual representation of that. An amine group, which means it has a nitrogen in that group, which is what amine means, which you're going to find this in nucleic acids and proteins, or amino acids. There goes the name amine, which means it has a nitrogen base in there. Like alanine, which is an amino acid, it has that amine functional group in there. This is what makes it a amino acid or amine group. Phosphate, if you look here, you have all these oxygens, which we understand oxygens to be very electronegative. So that means that they have a negative charge or a strong pull. We can find these nucleic acids, phospholipids, and then also in ATP, which is our energy molecule, which we'll see in the next chapter. And this is essentially what some of our DNA looks like right here. So we always think of DNA as being this nice helical structure, but chemically it actually looks like this. But this entire molecule here is what's called ATP, which is our energy molecule that our mitochondria, or our powerhouse of our cell, actually produces. So if we were to start putting some of these together, or in order to put some of these groups or carbon, hydrogen, or hydrocarbons together, we have to use some reactions. So you can have dehydration synthesis or hydrolysis. So dehydration is what it sounds like. When you dehydrate something, you take the water out of it, all right? So if we want to bring something together, you see that there's two hydroxyl groups. So what's going to happen here, you see that it's going to put these two monomers together to make a dimer. But in order to do that, it's going to bond these hydroxyl groups together and get rid of water. So if you notice, we have two hydrogens and two oxygens. So those two hydrogens and this oxygen are going to bind to each other and then get released. And then what's left over is that one oxygen, and it's going to bring those two together. That is called a dehydration synthesis. When you synthesize something, you're building something, you're making something, you're synthesizing it. Now, let's say we want to get rid of these or break these apart. We're going to add water to it, which is called hydrolysis. Hydro, that prefix means water. Lysis means to burst or to break apart. So it's doing exactly what it's saying. It's using water to break something apart. So we're going to take this dimer, which is the two monomers that are stuck together, and we're going to add water to it and break it apart. So literally it's just the reverse of dehydration. So if you're dehydrating something versus hydrating something, there you go. So here are some lipids, some other biological molecules. So we know lipids as being oils or fats. So one common one that's found in us is triglycerides. It's also found in triglycerides, phospholipids, steroids, and eicosanoids, which are the four primary classes of lipids. So triglycerides, if you take that word apart, tri means three. So you have three fatty chains here. They function in long-term energy storage in adipose tissue. So essentially when you eat a big meal and then your body either gets rid of it or stores it as triglycerides. So it actually has a structural support for cushioning and insulating the body, especially in the wintertime. And phospholipids, which make up that phospholipid bilayer that we mentioned a few pages ago. This is the actual chemical component of it. This is what it actually looks like. Usually we draw these nice little pictures of it with a nice head and then two tails, but this is actually what it looks like underneath the microscope. So you notice that these fatty acids, or these two chains here, were actually very hydrophobic. So now you understand, because they're fats, those tails, they don't like water. So that makes that bilayer. That's why water can pass through the bilayer. Steroids, when we think of steroids, we think of those big bodybuilders So that is a type of steroid, but that's not the steroid that we're talking about. So steroids, well, our body makes steroids from cholesterol, which cholesterol gets a really bad reputation. We need cholesterol. We need to be able to make our steroids or our hormones. So the hormones that we make from cholesterol would be our testosterone and our estrogen. And men and females have both. They just have it in different quantities, but they have both. Cholesterol is also good to have within the cells. In order for the cells to remain fluid and stretchy, they have to have cholesterol. Just like fish in the wintertime, when it gets really, really cold and the lake freezes over, by them having cholesterol in their cells, they're actually preventing themselves from, or preventing the water in their cells from freezing. This is why cholesterol is a good thing. Cholesterol gets a really bad reputation because there's two different types of cholesterol. There's a good cholesterol and there's a bad cholesterol. The good cholesterol is the one that we need in order to make our testosterone and our estrogen. However, the bad cholesterol is the one that's actually going to get stuck to our inside of our arteries and get clogged and can potentially cause us to have a heart attack. So not all cholesterol is bad cholesterol. But in the case of steroids, steroids are composed of 4 rings, which means that these carbons are in a circle-like structure. Steroid hormones are regulatory molecules released by certain endocrine glands. Bile salts are a type of steroid as well that helps break down our fats. Eicosanoids, which are these interesting looking molecules here, but they have a very vital role when it comes to signaling within our body. So our immune system is very alert to these. So like things like prostaglandins, which is classified as an eicosanoid. So when your body is experiencing pain, it's releasing prostaglandins or releasing these. That is actually what's actually binding to those receptors and telling your brain that you're in pain. So these are very, very important, where if there is some type of foreign antigen that's in your body, it's also going to be in a response to fighting that. So this is very, very important for our body to have. So these are the 4 basic classes of lipids. Another way to look at lipids, there can also be a saturated and unsaturated. We've kind of heard of those when looking at nutrition facts on the back of packages. So a saturated fat means that there are no double bonds. So if you look at this middle structure here, you see that these carbon and hydrogens are nicely stacked. They are very, very neat and pretty. So you can think of this being like a stick of butter. They're very, very nicely stacked. It's a nice little block. There's no imperfections. However, if we put a double bond in it, these are not able to stack. When you put a double bond in between 2 carbons, it kind of makes the carbon chain turn and kind of kink. And so it doesn't allow those molecules to stack on top of each other as these are able to stack on top of each other. So because it's not able to stack on each other, they're not able to, they're essentially moving all the time. So if you have a double bond, it's going to be more like a liquid. So think about vegetable oil. Vegetable oil has a lot of double bonds because they're not able to stack on top of each other. However, if you use margarine, which is just vegetable oil in a solid form, they just take out the double bond and make it this. That's the difference between margarine and vegetable oil. It's just a simple double bond. Now, margarine is not the same as butter. Butter is from a cow and it's from milk, versus margarine is actually from vegetable oil. Also, in order to change a liquid to a solid or a liquid oil to a solid oil, you have to give it hydrogen to break this double bond. So if you've ever fried food and you notice when you come back, the very top layer is solid, but the bottom layer is still liquid. You've essentially, what you have done is hydrogenated that oil. And so you essentially broken these bonds, this double bond, and hydrogens have taken its place and it started making a solid. So that's what's actually happening when you fry food and then you come back when it's cooled down and that fat is actually solidified. So you essentially remember, heat will break these bonds. Just like when you're boiling water, it will break these bonds. So when it comes to carbohydrates, so we think of carbs as things like potatoes and mashed potatoes and breads that are carbohydrates. But what is a carbohydrate? So carbohydrate just means it's a hydrated carbon. Nearly every carbon that's in that ring is hydrated with the equivalent of a water molecule. So that just means that there is an H and a hydroxyl group that is attached to those carbons. So let's go up here and find glucose again. So you look at glucose, each carbon has an OH and an H. So if you put H2 together and O, you get water. So a carbohydrate, when they say it's a saturated or it's water saturated, it just means that it has the molecules necessary that can make water. So you have this carbon has 2 H's and an O, this carbon has 2 H's and an O, so on and so on. So that's what essentially a carbohydrate actually is. Now, glucose is a 6-carbon ring, also known as hexose. Is a carbohydrate that is the most common monosaccharide. So if we say mono means one. Disaccharide, which would be 2 monosaccharides put together. And if you have many disaccharides put together, you have a polysaccharide. So simple sugars would be monosaccharides. The sugars that we eat, which is sucrose, would actually be disaccharides. So let's say we have eaten Thanksgiving dinner and we have a bunch of glucose just lying around in our body. So what our body is going to do is going to go through a process called glycogenesis. So glyco means sugar. Genesis means creation, just like in the Bible, it means the creation. So if you put this two together, you have glyco, which means sugar, Genesis means creation. So we're creating sugar essentially. Or what we're actually doing is building sugar. So if you notice here that it's putting a bunch of these glucose molecules together, it's just linking them into a big chain, what we call glycogen. Now, glycogen is actually stored within our muscles and within our liver. So if you go to a store and buy a steak and you see the marbling, that's actually glycogen. Our muscles are storing glycogen. That's fat and glycogen together. Now, let's say that you haven't ate breakfast or you've skipped breakfast and lunch. Your body is going to go through something called glycogenolysis. Remember, lysis meant to break down or separate. Glycogen, which is this molecule right here, is being broken down. So that's what glycogenolysis means. So essentially, glycogenolysis is going to take this glycogen molecule and separate it and break it apart back into glucose molecules for your body to use. So this is essentially what's kind of happening in your metabolism. So you have anabolism where it's building up, and then catabolism where it's breaking down. So now that you understand, this is a better representation of how metabolism is actually working. So examples of monosaccharides would be galactose and fructose. Fructose is actually the sugar that we have in our fruits. So the fruit, when you taste an orange and it's nice and sweet, you're actually tasting fructose. Ribose and deoxyribose, which that might sound familiar to you, that's actually those sugars that are actually in our DNA. And yes, our DNA has sugar in it, or it's made up of sugar. Disaccharides are monosaccharides put together. So sucrose is a combination of glucose and fructose. Lactose, which we hear of in milk, which that's the sugar that's in milk, is lactose and glucose put together. So if someone's lactose intolerant, that just means that their body does not have the enzyme to break these apart or to break this sugar apart. And so those bacteria like to feast on this lactose molecule and make a lot of gas and make your stomach more bloated and makes you go to the bathroom. So essentially, if you're lactose intolerant, that means you're lacking the enzyme lactase, which breaks this apart. And then maltose is essentially malt sugar, which is found in grains. So like malt liquor or liquor that is made, or like corn whiskey or moonshine, the maltose is the sugar that the bacteria is feeding on that's making the alcohol. Starch is a polysaccharide that's found in plants. Glycogen is the polysaccharide that's found in animals. So when we eat a lot of starches, we're eating essentially the glucose or the glucose of plants. And then when we're eating steak, we're eating a lot of the glycogen. So here is just showing how the sugar ribose or deoxyribose is within the nitrogenous bases that make up our DNA or make up the backbone of our DNA. And now you can actually see how we know this pretty image. However, it's actually all of these put together. So you have your phosphate group, your deoxyribose sugar, and then your nitrogenous base. However, we use hexagons, but these are actually carbons and hydrogens that are linked to each other. So crazy to think how all that chemistry we started at the very beginning goes down all the way down to an atom, and it's all the way through us. So everything that's in us is made out of something off the periodic table. So when it comes to DNA, so you have nucleotides. So you have a nitrogenous base that has either a single ring or a double ring structure that contains both carbon and nitrogen. The pyrimidines, they include cytosine, uracil, and thymine. So you can remember this by the acronym of CUT. And then the double ring nitrogen bases are purines, and they are of adenine and guanine. So, or as we say, A and G, or AG if you want to prefer. And so those are the bases that make up of our DNA. So we mentioned earlier about the amine groups, which you see right here. So a protein is made out of amino acids. It's just a big long chain of amino acids and a carboxylic acid that we're seeing down here at the very end. So amino acids are linked covalently, which means that they are sharing their electrons by peptide bonds that form during dehydration synthesis reactions between the amine functional group of one amino acid and the carboxylic acid functional group of the second amino acid. So that's what you're seeing right here with the amine group and the carboxylic acid. So this is a protein that's being just linked together. So a small strand of amino acids that's usually between 3 to 20 are termed as oligopeptides, whereas a larger strand of amino acids are referred to a polypeptide or a protein. Glycoproteins are proteins with carbohydrates attached. So it talks about how this is found in our blood group. So if you think about your blood type, like you have A positive, A negative, B positive, B negative, AB positive, AB negative, and O positive, O negative, those are glycoproteins that are on the outside of those cells. And so those essentially are what are telling us what type of cells those are. So glycoproteins are very, very important. Your entire body is made out of proteins. So it's very, very crucial that those amino acids are formed properly. So when it comes to protein structure, they are made out of different amino acids. So here you see some of them. So it breaks them down into nonpolar, polar, and then charged. So like histidine, that is a big component of histamine. So it comes from this amino acid. So most of these amino acids our body is able to make, but some of them we have to include in our diet. Some of these, like tryptophan, is what is commonly found in turkey, which it used to be believed that by eating a lot of turkey, tryptophan made you sleepy, but not necessarily. Phenylalanine is amino acid. If you eat cabbage, or especially like red cabbage, that's like in coleslaw and things of that nature, it has a lot of phenylalanine in it as well. So, and then cytosine has sulfur groups in there. So people that have like curly hair, they actually have the protein or the amino acid cysteine because it has sulfur in there. Because if you've ever gotten a perm, and that smell that comes out of there is because it's breaking that sulfur down, or the disulfide bond, which talks about right here. So when it comes to making proteins, the sequence that they follow makes their structure. So also remember, structure determines function. That's very, very key to understand when it comes to proteins. Structure determines function. So if you change the structure, you change the function. So in a primary structure, you can think of this like a pearl necklace. They all follow single file behind each other. They're very single file, so it's kind of in a linear sequence, as it says. In a secondary structure, it's a little bit more complex. It is actually made out of sheets. So this is like if you took a sheet of paper or sheets of paper and started folding them together. Or you start making things like our DNA, where it starts to wind around. It has a lot more bonding that's happening in between the proteins or the amino acids. That would be a secondary structure. A tertiary structure has both primary and secondary structures in there. And you can see that here you see helical, and then you also see sheets. And then quaternary structure, it has all of them. And that in this you can kind of find like the hemoglobin that's in our blood that's attached to our blood cells. That allows for iron to bind as well as oxygen. That structure is a quaternary structure, and it's a very dense structure. If that is to become damaged, or it started to lose its structure, or it became unraveled, it would no longer be able to pick up oxygen. So structure is very, very important for function. So if a protein becomes unraveled or it breaks apart, that's called denaturation. So denaturation is a big fancy word for just saying that your protein has essentially unraveled or broken down. Sometimes this can be caused by a change in pH. So if that pH becomes too acidic or too basic, it can essentially cause that protein to break apart. So remember, our blood pH is between 7.35 and 7.45 on the pH scale. It has a very narrow range to be within. If the change of the pH of our blood becomes too acidic, it can actually start damaging our blood cells. Our blood cells are made out of proteins. If you raise that pH and make it too acidic or too basic, it can possibly damage our blood cells or actually other proteins within our bodies. If our body temperature gets too hot, temperature can affect how proteins are arranged. So think about it like this: when you crack an egg on a hot skillet, that egg white is first clear, but when it touches heat, you can actually see those proteins denaturing and turning white. But here's the thing: can you uncook an egg? You can't. So once you break those proteins apart and denature them, it's almost impossible to put them back together. So this is one reason why it's so crucial when you are having a high fever and your temperature gets too hot, your brain cells and your other proteins start breaking down. And if they break down, that means it changes their structure. If you change their structure, you change their function. So this is why pH is so important. So here it shows us a picture here with how our protein is nicely folded. However, when we increase the pH or decrease the pH, you break that bond, so you change the structure of it, and now that structure no longer is able to function properly. So this is what this is actually showing. And that wraps up chapter 2. Hopefully you learned something new.